Okay, so I am recording. I am presenting. You guys see that screen? I don't know if I show me. Bear with me for just a second because this actually won't take long. Oh gosh, it's not really gonna. That's not gonna help. Okay, so I'm gonna turn that back off because it's gonna weird me out. Okay, so I am here in the morning, okay, but I have a sub from 5th to 8th. I have no idea what I'm supposed to be doing, but I have a substitute. And so what I'm doing is I am presenting my screen. You guys are seeing my Google slide. Okay, so I just need to make sure I'm doing it right because I'm not used to recording myself without students in the picture. Okay, now I actually have this lesson, and I'm gonna turn my lights off just because I think it might make it easier for you to see. Oh, great, my air conditioning just turned off, so I'm gonna try not to super speed talk through this, but I just lost my air, and yeah, that's great. So this lesson is the last in the theoretical unit, which is over the theory of relativity. The engage, the focus question, the opener, you guys go ahead and go in there. And it just asks, in which direction do we think, it's not think anymore, do we know that we can travel through time? So your options would be both forward and backwards in time, just backwards in time, or just forwards in time. And then secondarily, it wants to know how could this happen? Now, if you were listening to me when I talked about how Interstellar got it right, especially if you've seen that movie, you know the answer. Now, remember, we can see the past, we can view it, but it actually creates a paradox if we go there. So I'm not gonna I mean, I have answered it if you've listened to me the last few days, but I want you to go ahead and take a couple minutes to go into the opener and tell me which way do you think, even though I've told you already, can we jump through time? And then how would we do this? And I'm just going to wait for like a minute or two, like I normally do. And then I am going to have to flip-flop between my Google Slides and my old PowerPoint presentation because it's animated the right way in PowerPoint and it's not in Google Slides. So I'm gonna flip-flop back and forth here at the very last bit. And since this is a recording, if I go too fast, because I have to get this done rather quickly, you're more than welcome to pause this and go back because it's on the YouTube thing. I'm not even sure who my substitute is. I don't know if they have understanding of Einstein's theory of special relativity or not. I'm going to assume that this individual does not. But that is what we are talking about. So Mr. Albert Einstein, he came here from Germany. It's a good thing that he did. And once he was here, way back in 1905, so a while ago, he published his theory of special relativity, which has an infamous equation, which says, and I should have mentioned this yesterday, that as things go faster to the speed of light, the slower that time must pass. Now we know that we can't go the speed of light, only light can go the speed of light, and only nothing can actually travel faster than the speed of light. Material particles like us, we can't even come close to what is called a relativistic speed. And I can't remember if I have something on the next slide because I don't even know what I did with my notes, but they are somewhere. Are they up here? All right, there is one more. So the infamous equation from Einstein is E equals mc squared. And what that means is energy, the capital E, which is measured in joules, is equal to the object's mass times the square of the speed of light. The speed of light is 1.3E8 meters per second. 3, move the decimal, 8 to the right, meters per second. Which just means that as the object approaches the speed of light, it must be converted into energy, which we are not able to do. So as they go faster, time actually travels slower. Material particles, which is us, things that are made of matter, solid, liquid, gas, and plasma, not light. Light is photons, light is pure energy. As they go faster to the speed of light, they energize. Light can do that. Photons can do that. Things that are actually made of matter cannot. Now, the interesting thing about light is it has what is called a dual nature. Sometimes it acts like a wave, like when it's traveling through space, which is energy. And sometimes it travels like a particle, which is what happens when it enters a solid, liquid, gas, or plasma. It depends on what it's traveling through as that dual nature that light has. Now, what's really important with this one is that everything is from your frame of reference or your point of view. That is sort of what controls how you are going to analyze this. All right, so we're going to go way back. The Greeks, their point of view, the earth was at the center, everything went around them. The sun seemed to come up in the same spot, and in the same spot, same thing with the moon. So that was geocentric. They called it a celestial sphere. We know that that's not the way it is. They were the first ones to record that down. They're the ones that get that. And like I said, we know differently. We know that everything actually does go, well, depending on your point of view, everything goes around the sun from that, but the sun is going around Sagittarius A star with the rest of our galaxy that's spinning once every 200 million years. No, I said that wrong. Once every 200,000 years. And the next thing, what the galaxies are going around, has a new term, and if I'm not mistaken, I built that into the notes. We're not quite sure what's there, but we know that we're hurtling towards it. So, in this case, if we're on the Earth, we're going around the sun. If we're standing on the sun, let's just pretend, magic school bus level pretend. We're standing on the sun, we're actually going around Sagittarius A star. If we're standing on Sagittarius A star, which we know we can't, but let's just pretend, then you're going to see us being pulled towards that central point in our portion of the universe, which may be the center of the universe. You're not quite sure. So the speed of the Earth. The spin of our Earth is 460 meters per second. We are hurtling through space around our sun at 30 kilometers per second. So even though you're sitting here, you're really moving at 460 meters per second, just with the spin. But simultaneously, we're being hurtled through space at 30 kilometers per second. So these things are going to add up. The galaxy is spinning at 220 kilometers per second. And then we're moving towards that central point. They call it the Great Attractor. We really don't know what's there. It is sort of well, that's an obvious name. They do that a lot in space. But all of the galaxies are hurtling towards this point, which is why we are going to cross paths with Andromeda in 4 billion years at 100,000 or 100, I cannot speak, 1,000 kilometers per second. So if you want to know how fast we're really moving, you would add all of these up. Now, I do know that the 460 meters per second is not in kilometers per second. But if you sum them up, that would actually be the speed of our Earth. That, well, really of us. That we know of right now. Now, is there something else that's beyond that great attractor we don't know? So in relationship to the cosmic background radiation, which is far back as we can see, we are moving in relationship to that because it's a different point of view at 390 kilometers per second. That is sort of like the expansion of the observable universe. But the CBR stands for cosmic background radiation, which we can't see further than that. All right, now, this is to simplify it. You're moving on a train. You're on a moving train. And you are walking from the, how do I have it worded here? From the front of the train to the back of the train at 3 miles per hour. So for you, you feel like you are walking at 3 miles per hour while you're in the train. But if somebody's outside the train and they see you moving, they don't just see your motion, but they also see the motion of the train. So when you add those together, then you're actually, well, from their point of view, you're going 63 miles per hour. From your point of view, you're only going 3 miles per hour. That is what point of view and frame of reference does in space-time. Like I said, if I go too fast, because I'm trying to take care of this before my room turns 90 degrees, you're more than welcome to just pause and go back and take a look at it. Because the notes are in Canvas. I'm going to go ahead and I had them already set out if you needed a paper copy. Now, once again, material objects, particle objects cannot travel the speed of light. I mean, at least right now we can't, maybe in the future. But the closer you go to the speed of light is what is called a relativistic speed. Really only light particles can travel at true relativistic speeds. Like we said with the Big Bang, only nothing can actually travel faster than the speed of light. Now space-time, if you're traveling faster, is going to be different for you than the thing that you left behind, because the faster you're traveling, and it's the travelers, the faster that you're traveling, the slower the time will pass for you in relationship to the people that were left behind. So if you come back, you don't look like you age as much to them, and they look like they jumped 20 years in the future, depending on how far you go and how fast you do it. So everybody is still aging in this situation. It's just the faster people, time is moving slower. They're still breathing, they're still eating, they're still going to the bathroom, they're still doing their daily functions. So are the people on the planet. The people that were left behind, because they are traveling at a slower speed in relationship to the people who left, time will travel faster. They're still going to age like normal from their point of view. Both sections are. Planet-bound people, the people that are left behind, time is going to pass faster. The people who leave, the travelers, time is always going to travel slower. And you're not going to notice this until you guys come back together to see that passage of time. And like I said, yes, Interstellar did get that part right. We are not going to learn these things because I hear, oh, what are these formulas that you keep talking about? So there is an equation for the dilation of time, the contraction of length, and the increase for relativistic mass. I'm not even going to remotely try to do this for you. But for those of you that are curious, these are the actual formulas to be able to do this. Don't worry about that. Yeah, we're not doing them. I'm not going back to that stuff. But simplistically, because I am doing this conceptually, I will show you how to do it algebraically. That's when I have to flip over to my PowerPoint. But the faster your space traveler goes, the more time is going to pass where they left from. The more stretched that becomes. Keep in mind, we can only go forward in time. We can't go backwards in time. You see the past. We see the past all the time. You go stare at the sun, that's 8.5 minutes ago. You go stare at Betelgeuse, that's 650 years ago. You can see the past, we cannot go to the past. We can puddle jump forward. So honestly, aliens come to visit, and we go, uh-oh, we jump on our craft, we go up and we zoom around the Earth or wherever, maybe we go visit Saturn, and we come back and 100 years have passed and everything's perfect. Or we come back and they've taken over. So we go back out, we zoom around a whole bunch, and we come back 500 years later and they're all gone. But you can't go back to where you came from. I mean, you can go back and physically visit the area that you walked on, but you're not going to be able to necessarily see the same people that you left. Okay, so yes, this is sound. We do this all the time with satellites in space. Our problem, we have a few problems. First of all, we can't go fast enough. Second of all, we don't have the propulsion system. It just doesn't exist. Now for satellites, yes, but for people, no, not really. We don't have force fields yet. If you slam into dust or tiny pieces of anything as you're traveling near the speed of light through space, it is going to tear holes through your craft. And you would die. So we're not there yet. Maybe in the future, maybe your generation. Like I said, we do it on a smaller scale. Who knows what we're going to be able to do? Okay, this is the one that I need to switch over. And I need to go to my PowerPoint. See if I can get this to, I'm going to have to go over and then I'm going to have to okay, so I'm going to stop presenting. And I'm going to present. Let's see what happens if I actually try to prevent. I don't think it'll let me do it. I'm going to have to share my screen. Well, because it won't let me do my screen. Let's see what happens anyways. Okay, so all right, I'm not quite sure how well you guys are going to see this. We're going to go through. If I have to come back and amend it in the morning, I will. So you have to know a couple things. We have to know, if I can get this to go correctly, we have to know two things. We have to know, is it, and these are always going to be inverse. So going out, if it takes twice as long for a rocket to go out in order to see flashes, then it would be half the amount of time going back. So if it's 3 times out, then it's a third back. But they're always inverses of each other. You also need to know how long, and I don't know if you guys can actually see both of these that I can on my screen, or if you can actually see the projector. I don't know how this is showing it to you. Okay, but so the rocket, you know how long? So the rocket goes for 2 hours. That's a total of 120 minutes. And we need to know how often it flashes. And that's be once every 6 minutes. That's what the light is actually being emitted from the rocket. So that means on Earth, if it's twice as long out, instead of 6 minutes, that's times 2, which is 12. So the Earth person sees one every 12 minutes. And then on the way back, that 6 minutes is cut in half. So on the way back, it's compounded and it's seen once every 3 minutes. Now we just need to apply this to what's going on. But the rocket does one every 6 minutes. 10 flashes out, 10 flashes back, goes for 2 hours, a total of 120 minutes. On Earth, towards us, no, away from us, as it's going away from us, it sees one every 12 minutes, back sees one every 3. So we're going to apply that. So 10 flashes, we see one every 12 minutes is 120 minutes worth of time from Earth. Coming back is still 10 flashes, but it's once every 3 minutes, which is 30 minutes worth of time coming back. So when you add those, the rocket's a total of 2 hours, but on Earth, it's 2.5. Because when you add 120 and 130, there's an extra 30-minute window of time. Now, if we flip-flop this, like I said, I don't know how well you guys can see these from my screen. Okay, but let's say that the Earth is giving the flash. The rocket still does a 2-hour tour. Okay, it's still, we've got going away and coming back. So you still have to have your frame of reference. So the rocket and the Earth is sending a flash every 6 minutes. The rocket's going to see one every 12 minutes out, and then half back, which is 3. It's still doing a 2-hour trip, but the Earth is actually shining the beacon. So going out an hour each way, 12 minutes that it's going to see it, is going to end up being 5 flashes as it's going away. And as it's coming back, you're going to divide the 3 minutes into the hour, the other half of the 2-hour tour, which is 20 flashes going back. That's the rocket side. So the rocket side sees a total of 26 flashes in 2 hours. On Earth, if we have 25 flashes that have occurred at 6 minutes each flash, it's still the same time frame, 150 minutes, which is 2.5 hours. So honestly, the perspective does not matter, because whether it's from the rocket or if it's from the Earth, as long as you know how long the trip was, in this case it's 2 hours, 1 hour each way, and you know how much longer it takes for the light to be received going away and coming back. Let's just say they're always inverses. So if it's 4 times longer going out, it's a quarter coming back. They're always inverses of each other. You can actually calculate the stretch difference between the two. And I know 30 minutes doesn't sound like much. And with the satellites, it's only a few seconds in difference between Earth time and space time, but it does still happen. Now, I'm going to get off of this. I am going to stop sharing. And then I am going to go back to this. And if some reason that did not show right in the morning, I will redo this. I'm going to stop the recording. You guys have the assignment that goes along with this. I don't have any cool videos to embed in here that I can think of. If I can think of some in the morning, then I will. Behave, finish this. This should have gone a lot shorter with me just presenting it. If you need to go back and rewatch, you are more than welcome to.